Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at how we can use rate laws to determine the rate of reaction with respect to essentially the concentration of the species. So one of the unfortunate parts about rates of reaction is that it's often very difficult to try and figure out what the rate is based just on this strict chemical reaction. However, we do know a couple cool things. First of all, we know that it's dependent upon the concentration of the reactants, and it should be proportional to some sort of mathematical feature of the products present. So specifically, we know that it is most likely going to be some sort of product of the reactants to a given power. So in this case, the proportionality constant is given the variable k, and this is going to be our rate constant. Our exponentials, here x and y, are called the reaction orders. These are most typical integer values going from 0, 1, 2, 3, and 4. However, 0, 1, and 2 are by far the most common. And so if I go ahead and combine these ideas together, what we have is a generic rate law, where the rate of reaction is going to be based on some product of our reactants to a given power times some sort of generic rate constant. So one of the big things we're going to be trying to do is determining how we can figure out the values for our rate constant and our orders of reaction. So it is worth noting that this usually starts by first determining the orders of the reaction, as this is going to be the real driving feature, figuring out which reactants we have and how much they play a role in the concentration. Is it simply a first power, or is it going to be some sort of polynomial, which means it has a very big outsized effect? And this is often done by using experimental data, where we essentially change the concentration of a single species and then look at how the reaction rate changes. Does it simply double, triple, or quadruple? And this is essentially known as using the law of exponents. So if I say doubled the concentration of A, if the law's rate is first order, I'd expect the rate to double. If the rate is second order, I'd expect the rate to quadruple, because 2 times 2. If the rate is third order, it would be to the 8th. If the order was the 4th, it would be to the 16th, and so on and so forth. So again, showing that if you have a higher rate order, you're going to increasing the concentration will show an outsized effect on the speed of the rate. So this is a little bit arbitrary. So let's go ahead and try and apply it to an example reaction. So let's say I have this reaction where A plus B goes to C and D. So I'm going to go ahead and do this by tracking my initial rate of reaction with respect to the initial concentration of A and B. So let's go ahead and first look at when B essentially stays constant. So if I double the concentration of A, so going from here to here, I watch my rate double from about 3.4 to about 6.8. So this means that this is going to be first order. Now, we can also double check this as we go with the higher concentration of B. Again, I double my concentration at A, and again, the rate doubles again. So this is very consistent. Now let's go ahead and take a look at B. So this time, when I double the rate in this first time, the rate quadruples. So this means I've got a second order reaction with respect to B. And again, we can see this here. I double the amount of B, and the rate again quadruples. It goes up a lot. So essentially 4 times as fast. So this means the reaction is what's called first order in A and second order in B. And this gives us our overall rate law. Again, our rate constant times A to the first power, B to the second. However, most of the time, this is essentially just truncated, where we drop anybody who's just the first power. And if anybody's the 0th power, we just omit that reactant entirely most of the time. Well, so that helps explain how we figure out the rate order. But what about that rate constant? So one of the first things to watch out for is what will be the units of this arbitrary rate constant. And here, a useful thing to keep in mind is that our rate, as we saw last time, typically has units of molar per second. And so we're going to have a slightly different units of our rate constant depending on the order. So for example, if I have a 0 order reaction, well, then my rate's just equal to K. So all of the units have to be carried by K. However, if I'm first order, my rate's equal to the rate constant times a concentration. Well, in this case, the molarity units come from A, and K, my rate constant, just has to bear units of per second. However, fun things start happening when I get to second order, because now I've got molarity squared, and I need molarity per second, which means I need to cancel out one of those molarities, and I need to tack on that per second. So we're going to typically have units of per molar per second. So again, rate constants will always, so when we're looking at these rate constants, keep an eye out. They'll usually have units of per second, but occasionally you'll see per minute or hour. And their relationship with molarity is always based on the order. Another very cool thing about the rates is they will always give the rate if all of my reactants are 1 molar. So if I've got 1 molar A, then my rate is my rate constant, no matter whether X is 0, 1, 2, 3, and 4. So that's essentially a good idea for the physical meaning of the rate constant. Related to that is a very important feature. In general, the larger the rate constant, the faster the reaction. However, this is only really fair if you're comparing species of the same order. Because of that unit peskiness, it's hard to compare rate constants of different orders and have a good feel for what they look like. So when we're trying to determine our rate law for a given reaction, I'm going to keep 3 big things in mind. First of all, the exponents in the rate law have to be determined from experimental data. I can't just look at a reaction and say, oh, my coefficient is 1, it must be first order. Sometimes it'll be 0 order, sometimes it'll be second order. You never know until you test it. And again, reaction order is always going to be based on reactants. That is the only thing that the reaction really ends up telling me for sure. I expect my rate to be based on concentrations of A and B, not C and D. If it is, it means that I probably missed a reactant. And the order of the reaction can be determined by comparing changes of the reaction rate as I change concentration. So again, one of the surest way to find order is see what happens if I double the concentration, what happens to my rate. So next time, we're going to delve in a little bit more into the details of what these rate laws mean as we talk about 0 order reactions. Until then, take care.